Me. Oh, not your name. So you'll win.
All right, welcome. Professor Tyler is not feeling well today, so he's asked me to sub for him. And today we want to talk about partial fractions. So let's take just a minute and, well, does he usually do homework questions at the beginning of class from the previous section?
He just asks if we have questions.
Do you have any questions?
And we usually don't.
And you usually don't? Okay. All right. Well, let me just ask if there are any questions. Think we're good? Okay. All right, so we got a couple people that just walked in on me here. So let's go ahead and get you an activity. I'd like to have guided notes for my students because I like to be involved in the class and working together. So you're not so frantically trying to take notes. I've got some of them here so you can help work. Okay.
How do we make the other Jonathan do that?
Ask nicely.
Oh, we have seen great results from saying please.
Okay. All right. So give that a try, and then if it's for the full semesters, to help defray the cost of printing, I have my students just pay buy a little $6 voucher, and that just pays for the print for the whole year. So that's just the way I roll. I'm slightly different than Professor Tyler. I am Jonathan Bodrero. I've taught here at Snow College for over 20 years. So yeah, let's get in on this. So partial fractions. I remember the first time I saw partial fractions. It was kind of scary, but hopefully today I can make it less scary than my introduction. So if we take and let's jump back to something that might be a little more familiar. Let's go ahead and just add regular fractions. So if I do 1/2 plus 2/3, how do we do that?
Multiply both common denominator. Yeah, get a common.
Oh, we need a common denominator, right? They're different kinds of fractions. So if we make 3/6 here by timesing this by 3/3, which is really 1, okay? And if I times the 2/3 by 2/2, which is still 1, so we've multiplied by 1, we get a grand total of 7/6. Okay, all right, so yeah, we've been able to do this since about what, 5th grade, 6th grade maybe?
Yeah, I just learned now. That's good.
All right, so one right now. Okay, Zach.
Sometime in the past.
So now here's where it gets a little bit tricky. What if I have you unadd the fractions?
Or there could be lots of different options.
There could be several different options, but there's usually an easiest option. So for example, if I tell you that I added 2 fractions and got 11/15, who are the 2 fractions that I added together?
6/15 and 5/15.
Okay. So he says 6/15 and 5/15. Could you write them in a simpler form?
Yeah.
Yeah? Okay. Oh, okay. 5/15 is 1/3 and 6/15 is 2/5. Okay. So we're going to be doing the exact same thing, but instead of just with real numbers, with basic fractions, we're going to play with algebraic expressions. Okay?
Yeah.
Yay, we can do this. All right. So let's try it now. Let's say that we have the quantity 6x minus 10 divided by the quantity x squared minus 2x minus 3. What we're going to do is do partial fractions on this. In other words, breaking down into its fractional parts. Okay? And we're going to give you a hint. Let's first factor the denominator. Okay, so if we hadn't noticed 6/15 and 5/15, we could have said back here, well, what things would make the common denominator 15? Well, that's 3 and 5, right? Okay, so we need some thirds and some fifths. So let's see if we can do this. So we've got 11/15, and we need to find out we'd have, I don't know, a thirds plus b fifths. Okay, so if we hadn't had Zach here, or no, Kate helping us out, we could say that we could take this guy right here and getting the common denominator. Okay, we could then see that, oh, hey, check this out. So 11 would have to be 5a plus 3b, right? And maybe we could do a little bit of work. Oh, that's in the way of the camera. There we go. So we could do maybe a little bit of work. Could I have A is 2 and B is 2? Nope, that wouldn't work. But what if I do A is 1 and B is 2? Would that make 11? Yep. So if A is 1 and B is 2, then we've worked it. Okay. And we didn't get Cade's magic answer. Okay. So we might not always have Cade with us. So if you notice that, we put the 1 in place of the A, and there's our 1/3. 2 in place of the B, there's our 2/5. And so our partial fractions is the exact same thing. So we're going to use that same technique, but now on the slightly harder problem where we have expressions. So if we've got this, what we need to do is factor the denominator. How does our denominator factor here?
X minus 3,
X minus 3 and x plus 1. So using what we've learned up here, we expect this to break down as, I'm going to write that already, since that's really what this is worth. I'm going to write this as something over x minus 3 plus something else over x plus 1. Is that okay?
Yeah.
So we're just doing kind of like what we did here. We factored our denominator and said, okay, these are got to be the two pieces. And then we just use math to push him through. Now, here's where we do just like we did up here. This is kind of hard, and we're adding fractions. It's best or easiest if you add fractions and you use a common denominator, right? Just like we multiplied by 5 over 5 and 3 over 3, which are each worth 1. So when we do that, we get 6x minus 10 over x minus 3 times x plus 1 is a times x plus 1 over x minus 3 times x plus 1 plus b times x minus 3 over x minus 3 times x plus 1. Okay. So in a sense, what we're doing is we're kind of doing this step right here. We had the uncommon denominators, and we made the common denominators by multiplying by 3 over 3 or 2 over 2. Okay. Now, here's where the magic happens. Okay. If we notice that the denominators are all 15, he can say, hey, what are some things that add up to 15? He says, hey, some easy things are 6 and 5, right? So, in other words, what we're going to do is we're going to take and we're going to multiply everything by x minus 3 and x plus 1. And what's going to happen? Bam! No more denominator.
Yeah.
Okay? So what does that tell me? It tells me 6x minus 10 is equal to a times x plus 1 plus b times x minus 3. And now we've got several choices. I'll show you two of the principal ways that we can handle this guy. Choice 1, let's go ahead and show you something that will help you out for a little bit later. We've got 6x minus 10 is equal to ax plus a plus bx minus 3b. So just using the distributive law. And I'm going to rewrite this as 6x minus 10 plus a plus b times x plus a minus 3b. In other words, I'm going to group on the x's, group on like terms. We okay with that? How does that grouping on like terms help me?
Gives you simultaneous equations.
Oh, it gives me simultaneous equations. If 6x minus 10 is equal to this right-hand side, then the coefficient of the x here has to be the same as the coefficient of the x there. So literally, a plus b is equal to 6, and the constant term has to be the same as the constant term. So a minus 3b is
Well, it's -10.
-10. All right. So we can solve that in a variety of ways. We could use a matrix from Math 1050, but this is simple enough that maybe I could just use some elimination. Okay. A minus A is 0A, so we just eliminated. B minus a -3B is 4B. And 6 minus a -10 is, careful, 16. So when we divide by 4, we find out that B is 4. And if B is 4, then A is 2. Okay. I need to zoom out just a smidgen. There we go. So I can say that this right here is worth, if I do I did which term first? X minus 3 first and the X plus 1 second, because that's the order y'all gave it to me. So the A is 2 and the B is 4. Wow, okay, I got a couple of, holy cow, what's going on here, Madero? Are you ready for some interesting stuff? So let's try something else. Let's try a web page. And let's do a new one. Let's pull up some Desmos here. Let's see. So I think I'm sharing my Desmos stuff. Let me make sure I'm sharing the right thing. Yep, I am sharing the right thing. Good. So let's get graphing. So let's go ahead and do y equals 6 times x minus 10 divided by x squared minus 2 times x minus 3. Okay, so we get this guy right here, and if I zoom out just a smidgen, you'll see him a little better. Obviously, you notice that we have some asymptotes here when x is 3 and x is -1, coming from where the rational function is not defined, right? That's where it causes divide by 0, and divide by 0, we don't do that. That destroys the work. Yep. So let's just, for fun, see what would happen if I did y equals 2 over x minus 3. That blue thing did not match up with the red thing. Let's do y equals 4 over x plus 1. That didn't match up with the red thing either. Oh, but what if we add them together?
Whoa.
Whoa, check that out. There's the original. There's our partial fraction decomposition. It is the same thing. It's unadding to break them up into his unadded fraction parts. Are we okay with that? Yay, all right. So let's go back to our paper here. Okay. So why the heck do we need partial fractions? Well, here's why we need them. What if you needed to integrate 6x minus 10 over x squared minus 2x minus 3 all dx? Okay. You might try u equals x squared minus 2x minus 3, right? You might try a u substitution. Then who's du dx? 2x minus 2. So du would be equal to 2x minus 2 dx. Is that going to give us a nice, easy, good fit here? No. So if we don't know partial fractions, we're stuck. Okay. But we do know partial fractions, so we can write this as equal to 2 over x minus 3 plus 4 over x plus 1 dx. Is that any better?
Yeah, because then we can take the integral of each one.
Oh, he says, let's take the integral of each one. And I'm going to factor out the 2, so we have 1 over x minus 3 dx. And I'll factor out the 4, integral of 1 over x plus 1 dx. Okay. Can we do this guy? What's his integral? Natural log of absolute value of x minus 3, right?
Yep.
Plus 4 times natural log of absolute value of x plus 1, and we're done. No?
No, plus c.
Very good. Okay, indefinite integrals plus c. Okay. Just for what if this had been an integral from, let's see, 4 to 10? Could I do that?
Yeah.
Yeah, we just take all of this and cut out the plus c because he'd be subtracting out anyways and go from 4 to 10, right? Okay, so we can even handle this on definite integrals. Hallelujah. All right. Okay, so let's see if you've got this. Let me give you a practice problem in a couple minutes to work on him. So x squared plus 5x minus 14. I hope. Still got a few pencils going. We'll give you another minute and then we'll come back together and work this one and see what you got. And then I'll show you another way that I told you that there were several ways. Here was one way. I like this way because it generalizes to other problems. I'll show you another way that works in special cases, okay, and can be slightly quicker in those special cases. All right, so help me out here. So we got 36. How does the denominator factor?
X plus 7, X minus 3.
x plus 7, x minus 2. Okay, so if he's going to break down into fractions, what are the fractions going to be? X plus 7 and x minus 2 on the bottom, right?
Yeah.
We don't know who the top is, so we're going to give them variable names, a and b. Okay.
And then multiply.
Multiply so we get a common denominator. And can I save just a little bit of space and do 36 is equal to a times x minus 2 plus b times x plus 7?
Yeah.
Would that be okay? All right. Now, we could do the distribution and then equate like terms. Wait, there's no x's over here.
So the x is
But it still equals 0.
Oh, so it's 0 x's, right? So 0x plus 36b. So we could still do it that way, just in case anybody got tripped up by that. But here, if these are what we call linear factors, okay, and they are not repeated, in other words, they're different, which they are, then you can use this nifty sneaky technique. What if I were to let x be, so let's take this guy right here, this equation, and let's suppose that x was equal to 2. Just suppose. What?
That's illegal. That's not ski on.
Okay. Well, it sort of is, so that's why I'm not telling him no. So, because is 2 allowed in the natural domain?
No.
No. Okay. But just pretend with me for a minute. So if we do that, we've got 36. Why did I choose 2? Why not 17 or negative 4?
Because it'll go to 0.
Oh, snap. That zeros this thing, doesn't it?
Yep.
Plus b times 2 plus 7. And 2 plus 7 is 9. 36 divided by 9 is 4. Is that what you guys got the other way?
Yep, that's what I got.
Should that be an equals, not plus? Right there, yeah.
Thank you. All right. What should I do to find out what a is?
-7.
There he goes. He says x is -7. So if that's true, then 36 equals, not plus. Throw a -7 in there. We've got a times uh-oh.
Oh no.
That's unfortunate.
I have some good news. I have
Yeah,
a
another
battery
PC.
cable.
That's
Woo!
much better.
Yeah.
So, hallelujah, we'll save this. All right. Okay, so, good, we're back. Whew. Okay, so we have a times -9, so a must have been,
-4. Oh, sorry.
is that right?
Yep, that's right.
Okay, all right, make sure that I'm doing things right. Okay, so if that's true, then our original thing, so we've got the integral of 36 over x plus 7 times x minus 2 in the denominator, dx, would be equal to the integral of who and what?
Wait, sorry, what?
-4 over x plus 7.
-4 over x plus 7 plus 4 over x minus 2 dx, right? Okay. Which we can do a couple of little baby steps here. Which is going to give us
The ln.
-4 ln absolute value of,
X plus 7.
good,
4 ln. X minus 2. Absolute value of x minus 2.
plus c, because it was an indefinite integral. Now, occasionally, you'll see a different form in the back of the book. Is this the same as natural log of absolute value of x minus 2 over x plus 7 all to the 4th power plus 8?
Yeah.
Use some properties of exponents. So we could take and factor out the 4. Then you're noticing this, actually the property of the logarithms, this negative here, I could combine with that natural log as a division, and then using the power property. Okay, so which way is right? Well, all of them. There just may be more than one format.
Where does the exponent 4 come?
From the 4 in the front.
From the
Oh,
4.
okay, okay.
So we happen to have a 4 here and a 4 here. Okay.
the
So that was
negative
really nice.
makes it go in the denominator, and then the 4 becomes the exponent.
But he's a 4 on this one, and he's also a 4 on that one. Yes, sir. Mr. Gage.
How do you know that the x plus 7 is on the bottom and the x minus 2 is on top?
Because of negative.
So can you still do that if they weren't both 4s?
So let's do
You
that
could do
in
like
steps,
4
just to
thirds.
clarify.
Okay, yeah, I went too fast. So let's do that in steps. So negative 4 natural log of absolute value of x plus 7 plus 4 natural log of absolute value of x minus 2.
Just factor it out.
Okay, let's factor out the 4. So we've got 4 times, and I'm going to write natural log of absolute value of x minus 2 minus natural log of absolute value of x plus 7. Of course, we've got plus c out here, right? Okay. Now, if we have natural log of a minus natural log of b, what's another way I could write that? Natural log of a over b, right? Okay. And what's the natural log of, what's p times the natural log of a?
ln of p to the, or a to the p power.
Okay. So let's do a couple more baby steps here, just to show how we're all good. So we've got 4 times the natural log of x minus 2 over, because this one's to subtract, so our property tells it's going to be, this guy's going to be in the denominator.
Yep.
Now, if this had been a 2 and a 3, I'd probably just have left it as is. Okay. But since we had a 4, that was nifty, and I could put it all here and save one symbol. Is that all right? Okay. So, are we feeling a little better with partial fractions?
Yes.
Okay. All right. So, sometimes they're nice and easy like this. But sometimes it's a little bit different. In this case, it was easy because the denominator factored into 2 separate, distinct, different linear pieces. Okay. What would happen if I wanted to decompose the fraction 19 over 27? Well, we notice that 27 is 3 cubed. So what are my options for the fractions building up? Well, I'd have thirds, ninths, and 27ths. Okay. So even Cade might have to stop and scratch his head here for a second. See if he can figure this one out. Okay. But using basically a similar technique, 19 over 27 would equal 9a plus 3b plus c all over 27, right? So could we maybe fiddle with this a little bit to find some a's, b's, and c's that are going to add up?
Yeah, probably.
Probably. Okay, so let's try something. Obviously, a can't be, well, ooh, could a be 2?
18.
Oh, hey, check that out. That'd be 18, and if c is 1 and b is 0, well, dang, we just stumbled right on top of that, didn't we? So if a is equal to 2, b is equal to 0, and c is equal to 1, bam, we've got it. Okay, but it might have taken us some trial and error. So that means that 19/27 breaks down into 2/3 plus 0/9. I'll go ahead and write that, although we wouldn't really actually do anything with them, plus 1/27. Wait,
No, maybe. Wait, could we have done 9 is a 1,
okay, so he's asking, what if a is a 1,
B is a 3, and
b is a
C
3, and c is a 1?
Yeah.
Okay, let's see what happens there. I like that. So we've got 1/3 plus 3/9 plus 1/27. That's a different answer. Oh, okay. So this would be 2/3. Oh, sorry, 1/3, which we could add to that and still get our, in simplest form, 2/3 plus 1/27.
So basically, just do it however and simplify it.
Now, yep.
Okay.
So
What do you-
here's the cool thing: if he's a partial fraction, you don't have to worry about these multiple things if you set him up correct. Okay? So he'll take care of himself. So let's try this guy, and then we'll integrate him. So once again, we've got 2x minus 5 over, wait, whoa, how's this denominator factor?
X plus 2, X plus 2.
Yeah,
X plus 2 times
X plus 2.
x plus 2.
So X plus 2 squared.
In other words, x plus 2 squared. Okay? So you can see that that factor, x plus 2, was repeated.
Mhm.
Okay? So here's where sometimes students get a little bit tricked. Don't get tricked. Okay? If we have a repeated factor, we need that repeated factor and every multiple of him, right? So I need x plus 2 and I need x plus 2 squared. Just like when we had the 27, what do we need? We need thirds, ninths, and 27s. Coming from thirds, thirds to the first power, thirds to the second power, thirds to the third power. Okay? Clear out all of the possibilities and deal with it later. Now, here's something that we need to focus on. The factor himself is a linear factor here. So the top is going to be something smaller than that, which would be just a constant. Now, I know that when we take a look at this, we say x plus 2 quantity squared, that is a quadratic. Yes, it was. But the factor himself, okay, even though he was repeated, the factor himself is linear. So the top is going to be a constant as well.
So don't get tricked there either.
What's that?
So don't get tricked there either.
Don't get tricked there either. And we'll talk about, yeah, in a couple more examples, we'll see a couple other things that we need to watch out for. Okay. So now what?
Now we multiply the left side by 1. Will be x plus 2 over x plus 2. And that's negative.
We've got 2x minus 5 is equal to a times x plus 2 plus b. All right. So 2x minus 5 is equal to a times x plus 2a plus b.
So A has to equal 2.
So he says a must be equal to 2, and then negative 5 is equal to 2 times 2 plus b. So b must be, let's see, so that's a 4. If we subtract 4 from both sides, b's got to be negative 9. So 2x minus 5 over x plus 2 squared is equal to 2 over x plus 2 minus 9 over x plus 2 squared, right?
Yep.
Now, what I like to do right here, just to make sure that I'm still okay, and I haven't made any, silly arithmetic mistakes. This expression is great for every number except for negative 2, right? So it's good for like something easy like 0. So I do a quick double check. If I put a 0 in for x, what do I get? So we'll do a thought bubble here. So if x equals 0, we've got
Negative 5 fourths.
negative 5 fourths.
Yep.
Okay. So let's do that thought bubble down here. So using this guy right here, let's do our thought bubble. If x equals 0, I get 1 minus 9 fourths,
Yeah.
which happens to be
Negative 5.
Negative 5 4.
negative 5 fourths. So do I feel pretty confident I didn't make a simple algebra mistake? Yeah, I feel pretty good. Okay. So those are our thought bubbles. Now, what do we need to do? We asked you to integrate.
Oh. Not that.
We ain't done yet. Okay? That's why there's still extra space, right?
On your paper.
On my paper. Oh.
Yeah. It's our paper.
All right. Well, can we integrate 2 over 1 plus, 2 times 1 over x plus 2 dx minus 9 integral of 1 over x plus 2 squared dx?
Yeah.
Yep.
Get 2
So we'll get 2 ln absolute value of x plus 2, he's saying over there. Do I get, hey, yikes, what do we do here? U substitution. U equals x plus 2 du equals dx, right? Okay. So I'm going to show my steps because that caused a little bit of confusion earlier. So we've got 9 integral of u to the negative 2 du, right?
Yep.
Okay. And is it okay if I take the plus c for the very, very, very end? I know technically he came right here, but we're going to get another plus c. But plus c is plus c. Different c. Good. All right. Okay, so we've got 2 natural log of absolute value of x plus 2 minus 9 over what? What's the antiderivative of u to the negative 2?
Oh, divide by, it'd be
U to the negative 1 over negative 1, right? In other words, negative 1 over u.
Yep.
Uh-oh. But was a u was something we did to the problem.
Yeah.
Okay, so let's fix that. 2 natural log of absolute value of x plus 2 plus
9 over x plus 2 plus c.
there you go. Take a impossible or at least a hard problem and make it manageable. Okay. All right. So Pete, turn the page. Let's do this. So what if we have stuff in the denominator that is not linear, but it's quadratic? Well, as long as we keep things proper, we're good. So you're okay that our dummy variable can be x, but it can also be s. Okay? So let's see what happens when we have this guy right here. S squared plus 4, does he factor? Not over the real numbers, right? He factor over the complex, but not over the real. What about s squared plus 1? Nope. So we're going to pull a similar trick here, but since these factors are no longer linear, but they are quadratic, okay, we're going to need to make a small change. So we're going to do kind of like just what we did. We're going to have our factor pieces here, but since this bottom is a quadratic factor, the top doesn't have to necessarily just be a constant. He could be a linear term. Okay. Similarly, this guy could be a linear term. But the good news is we're going to play the same game again. Okay. So we're going to multiply by our magic 1. And if I do that, we're going to get 2 equals as plus b times s squared plus 1 plus cs plus d times s squared plus 4. All right. We could multiply that all together. Or I could do some substitutions, right? Okay. If I let s be 0, would that make life be a little easier? Or s equals 1, or s equals negative 1, or s equals 2? Would that give me a system of 4 equations and 4 unknowns? Yep.
Yeah.
Okay. What else could we do? 2 is equal to, let's just go ahead and do it the other way. As cubed plus as plus bs squared plus b plus cs cubed plus 4c s plus ds squared plus 4d's. Now 2 is really 0s cubed plus 0s squared plus 0s plus 2, isn't it? So let's go ahead and group on the s's. So who's the coefficient of s cubed? A?
C.
Oh, what I do is I underline them so I don't accidentally forget somebody. All right. Any s squareds?
Yeah, B and D.
Okay. Any s's?
Yes, A, C.
A plus 4c. And finally, b plus 4d is our constant term. So literally that tells us that a plus c equals 0. B plus D equals 0. A plus 4C equals 0. And B plus 4D equals 2. Okay. Now, we could take that system of equations and we could put it into a calculator, put it in a matrix, yada, yada. But let's see if we can maybe save ourselves just a little bit of time. How about I eliminate on these two guys? So how about I take the second row and I subtract the fourth row? That'd be okay?
Yep.
So b minus b is 0b. We eliminated the b's. D minus 4d is negative 3d, right?
Yep. 3D equals negative
And 0 minus 2,
two.
so d equals
2/3.
2/3. Dang. Well, that's going to be hard. Now I've got to go find 3 other guys. But I'll give you a hint. B equals what?
3/2.
Close.
Oh no, negative 2/3.
Negative 2/3. Okay. All right. How about we play a similar game, but with the first and third equations?
0.
A minus A is 0. C minus 4C is negative 3C. And 0 minus 0 is 0. So negative 3C equals 0. So C's got to be 0. And therefore, A has to be
Negative 0.
negative 0. Also known as 0. Thank you. So what do we got? We've got that this guy is going to work into, we've got A is 0, B was negative 2/3, so we'd have negative 2/3 times 1 over s squared plus 4 plus C is still 0, and D is 2/3 times 1 over s squared plus 1. And could we do some maybe like trigonometric integrals here? Please no. Okay. All right. I'm going to pause there and let you finish with those. Just take and integrate that guy, right? ds. Because I need to teach you one more thing for today. And we've used him implicitly all day today. But what's an improper fraction? Who can give me an example? 7/3. When the numerator's greater than or equal to the denominator, right? So the numerator is greater than or equal to the denominator. Okay. Now, every one of the problems that I've worked with you so far today has been a proper fraction to start with. Okay. And this technique that we've just developed together here works on all proper partial fractions, okay, or rational functions. So, oh snap, what happens if I run into this bad boy right here? He is a higher degree on the top than the bottom. Then I can't use my partial fractions to break him up.
Flip it around.
Flip it around. I wish we could, if it was that easy.
Panic.
Panic. Nope.
Give up. That's
Give up. Yeah. No. Here's the key. So what we're going to do is we're just going to take and. Okay. So 7/3 is really 2 and 1/3. But where the heck did the 2 come from? You divided the 3 into the 7 to see how many times he went in, how many whole times, right?
Yep.
And then saw the remainder. And the remainder is a proper fraction.
Whoa.
Whoa, hey, we're going to do the exact same thing right here.
Oh,
nice.
Oh, so x squared minus 2x minus 3. We're going to long divide him into the numerator.
That'd be cool.
See what the whole number part is, and then just play partial fractions on the remainder. Okay, so how do I make an x squared look like a 2x cubed? Total timesing by a 2x. So 2x cubed minus 4x squared minus 6x. And please don't shortcut me here. This is where most students make the mistake. Subtract. Write that subtract sign. This is where the most common mistakes are. So by design, 2x cubed minus 2x cubed is 0x cubed. Okay? Negative 4x squared minus a negative 4x squared is 0x squared. Oh, snap. That is great. This must be our first kind of example of this kind of problem. And then negative x minus a negative 6x is 5x. And how do we long divide then? Minus 3, right? So literally, this nasty looking thing is really 2x plus 5x minus 3 over the remainder, right? And the remainder happens to be a proper rational expression, right? Rational function. So what do we do here? This guy's even easier because to integrate this, bam, I can do that. I've been able to do that since about the, what, 3rd week in Calc 1? Right? Maybe 4th week? Okay. So all we have to do is focus on partial fraction decomposition of the remainder part.
Yep.
Okay. We've got a minute and a half. Let's see how much we can do before time runs out on us. So we've got 5x minus 3 over x minus 3 times x plus 1. Okay, oddly enough, that's going to break down into x minus 3 and x plus 1. And those are linear factors. So what's going to go in the top? Constants. Okay, so when we had quadratic factors here, degree 2 factors, what goes in the top? 1 less degree. Okay, and that's because we're dealing with proper fractions. Okay, 5x minus 3 equals a times x plus 1, bless you, plus b times x minus 3. And I'm going to do the little trickiness. I'm going to say x equals 3. So we get 15 minus 3 is 12 is equal to 4a. So a had to have been 3. Let's let x equal negative 1. Negative 5 minus 3 is negative 8 is equal to, bam, this guy goes bye-bye, negative 4b. So b must have been 2. So this nasty looking thing becomes a whole lot easier. 2x plus 3 over x minus 3 plus 2 over x plus 1 dx. And we got 15 seconds. We can do this. X squared plus 3 natural log of absolute value of x minus 3 plus 2 absolute value of x plus 1. And indefinite integral, make sure you get your plus c. Booyah!
Learned.
All right.
Speed man.
Okay. hopefully Professor Tyler will be back very, very soon.